One question, Raghavan, will there be a tea break or not?
Yes.
Yeah,
Yes.
that's for today too.
There will be a tea break.
At
No, I mean at CMI.
Oh, at CMI you mean?
no, just now.
Here.
Yeah, yes.
Yes,
That-
at 11:45.
Yes,
or?
that's what I've just reminded them that 11:45 they should get some tea.
Okay, so I will have a break like usual.
As usual, yes.
Okay.
Yeah, it's just a usual format.
Okay, good. Thanks. So, so today I think I will talk about moment graphs and how moment graphs appear in this picture. So they are equivalent to Sergel bimodules whenever these two theories make sense, but they give a new kind of a local view on the problem. So so I explained in the last lectures that the main problem is to decompose a certain tensor product of bimodules, of Sergel bimodules. So these are bimodules over a symmetric algebra. You form this tensor product, and then you want indecomposable summons. This is also kind of possible in the moment graph theory, but you can construct the indecomposable objects in the moment graph theory directly without using translation functors. So this is a kind of new viewpoint on the theory. And so let me start with connecting moment graph theory to representation theory. So, yeah?
Could you please repeat that indecomposable, whatever you said once again? I didn't quite catch it.
All right, let me...
Global bimodules.
Right. So let me write it down. So the decomposition problem So let me define this problem without referring to representation theory, or it's just stated as a as an exercise, if you want. So we have the symmetric algebra. S is the symmetric algebra over the Cartan. It is useful to sometimes think of this as the symmetric algebra over the, say, the co-weight lattice tensor C. Because here you see I could easily change the complex numbers to any field and just write down the same problems. You can replace complex numbers by rationals or by any finite field or whatever you want. So, but this comes with an action of the Weil group, because there's a linear action on the Cartan, and this extends to an algebra, an action by algebra automorphisms. So for each simple reflection, or I mean for any reflection in the Weil group, but we will only need the simple ones, you define the invariance. And now the category of Sergel bimodules is the following category. Let's call it B. This is the full subcategory of the category of S bimodules that contains direct sums of direct summons of the Bott-Samuelson bimodule. Let me define it as follows. So of BS, this stands for Bott-Samuelson. Bs S1 to Sn, which is the following S bimodules. So you take this tensor product over the invariance of S1, and then you go on and you take the invariance over the tensor product with the invariance for Sn. This is an S bimodules, one copy acting from the left, one copy from the right. Yeah, I will explain it in a second. And so this is the category of circle bimodules, and it's now very important to consider this as a graded category. So the grading is usually defined as follows. So S is an Z-graded space where S1 is just the Cartan. Sorry, S2. S2. We want to have this. We want to this in degree 2 generated. So this is evenly graded, and then we allow shifts of Bott-Samuelson modules, and this is the direct sum of graded. So graded S bimodules. So it's easy to consider this as a graded category, but this grading is invisible if you come from representation theory. So before I explain the name Bott-Samuelson, let me write down Zergel's theorem. Okay, for each W and W, there is a unique.
So the grading is left bounded on any given object.
Yeah. Right. Right. They are right. For each W in W, there is a unique object. So unique up to isomorphism, of course. Let's call it BW, B of W in this category B with the following properties. So it's indecomposable. Now, two conditions that I explain in a second. So the support of BW is contained in the union of gr x, where x is smaller or equal to W. I explain this in a second. And third, BW restricted to gr W is isomorphic to S, not shifted. Let's be a little. Let's shift this by length of W. So to be consistent with other papers. So what is gr x? So I mean, what is an S bimodule? There's nothing than a coherent sheaf on H dual cross H dual. So the symmetric algebra S is the symmetric algebra of the Cartan, which is just the space of the algebra of regular functions on its dual, and so in fact, all these bimodules can be considered as coherent sheaves on H dual. And now if X is in W, you define, sorry, so what did I say? So S tensor S is the functions on this product. So, okay, an S bimodule is nothing else but a coherent sheaf on H star cross H star. And gr X is just the twisted diagonal. So this is the space of elements lambda, X of lambda. So this is for lambda in H dual. And this sits inside this product. So it turns out that the Zergel bimodules, or these Bott-Samuelson modules, they are supported on a union of these twisted diagonals. And so these conditions make sense. I mean, if you look at the empty expression here, this would correspond to S as an S bimodule. So the easiest Bott-Samuelson module is S itself, considered as an S bimodule. And this is the space of regular functions on gr E, so on the diagonal in H dual cross H dual. But then if you form these tensor products over the simple reflections, you get in the end a coherent sheaf supported on a union of these twisted diagonals. And there's a unique one, which is indecomposable, which has a support lying inside here, and where the restriction on this kind of extremal twisted diagonal is just free of rank 1. Yes?
I understood you correctly. You were saying that it is conjectured that this is sort of the categorification of the Ashtan polynomials.
Right. So let me come to this now. We have these indecomposables, and secondly, so the second part of the theorem of Zergel is that each object in B is a direct sum of shifted copies of various BWs. So these are the these from the isomorphism classes of indecomposables up to shift. So now, what is the connection to the Hecker algebra? So the kind of standard objects in the category of S bimodules for our in our situations are objects called let's call them delta X. And delta X should be so the functions on gr X on this twisted diagonal. So in other words, delta X is just free of rank 1, where the The left action is just so the usual left S action, and the right action is twisted by X. So an F in the symmetric algebra acts as multiplication by X applied to F. So now, consider the homomorphism space in the category of S graded as bimodules from delta X to, say, some BW. So, but consider this as a graded space. So the degree 0 homomorphisms and degree 1 homomorphisms, degree 2 homomorphism, and so on. And let me define it like that. So the degree n homomorphisms are the degree 0 homomorphisms from delta x to BW shifted by n. Let's define it like this. So this is a degree shift, and define the character of BW as follows. And I have to say, here I'm a little unprepared. I'm not sure if I get the grades. Huh? I think I mean n. So where this is defined, so m n in degree I is m I plus n. And so this means that, for example, if you look at the homomorphisms from S to S, they are non-zero if, or maybe, okay, that, yeah, right. Non-zero if n is positive, is non-negative, if I'm not mistaken. So let me see if here I'm a little unprepared because I'm pretty sure that I get the powers of some gradings. I mix up some gradings, but so let me see if I find the right normation. Now I think I have to look that up. So up to normation, you define the character of BW as follows. So you sum over all x in the Y group. Then you sum over all integers. Then you take the dimension of this Hom space in degree n. From delta x to BW n, and then so this should be an element in the Hecke algebra, which has this standard basis and the index by x. So this is not the self-dual basis, but the standard basis. And then here is a factor of v. And please allow me to put a question mark here. I can look that up if you want to have the precise. I can tell you where the precise formula is. I don't remember, but I mean it's not so. So of course it's v to the, let's say it's v to the n plus something. It depends on n. Say it again.
Left-hand side is, what is V?
Oh, a Q. V. So this is an algebra. So this is. So V is the square root of Q.
The definition of character is for any, the definition of character could be for any Sorgen binomial, not just beta.
Yeah, of course. Yeah, of course, absolutely. Right. Oh, wait. I'll get. I think I made a mistake here. Wait. So I'm sorry. I was prepared for the moment graph theory, and here there is a there is a slight mistake. Is that true? Because this can be a non-zero for infinitely many I'm sorry. Now I'm a little confused. I mean, if X and W are the identity elements, you have S as an S bimodule here and S as an S bimodule here, and this would be an infinite. It would actually be an infinite sum. Okay. Sorry, it's a slight. So under the slide, there's a mistake here. There's a mistake here. What I want is the rank of Hom. So as a graded S module, the graded rank. So it's V to the question mark, and here's the graded rank of the following. So I take this homomorphism space, but I take all degrees, and this turns out to be a graded free S module. This is a graded free so it's isomorphic to some to a direct sum of S shifted by some Li's. Let's write it like this: shifted by N and some multiplicity Ln, and the rank of such a bimodule is then the sum of Ln V to the N. So the rank is this polynomial. Sorry, I made a mistake. Let me say it again. So yeah.
And so then the sum over the N that should go.
Say it again.
The sigma second sigma.
Right.
In some sense, I mean, you wanted to pull the rank out.
Right. So if I look at the dimension, I mean, I have to look at this space in all the ranks, and it turns out it's a free. That's another theorem that it's a graded free S bimodule, and then you can look at the graded rank, and this is a finite polynomial, and then you shift by some number. This is probably length of W minus length of X or something. And then you get an element in the Hecke algebra. So, and this is up to normation. As I said, there might be some normalizing properties. So, okay, anyway, for each Zergel bimodule, you obtain an element in the Hecke algebra, and now there's another theorem of Zergel. So that is the categorification theorem. So note that so the character, I just write it down what it means. This is an algebra isomorphism from the Grothendieck group. So B is a tensor category. So that is the Grothendieck group, and it's an algebra using the tensor structure of B. So tensor structure yields so makes this into an algebra, and the grading just means it's a Z v to the minus 1 algebra. The character is a map into the Hecke algebra, and this is an isomorphism. This is an isomorphism. And it has the property that, for example, BE, this goes to the unit. I mean, this is the unit. That is just S as an S bimodule. This is the unit. So the unit in the Hecke algebra. And for example, this BS, which we defined as S over the invariance, S shifted by, so we need this shift by 1 to make it self-dual. This goes to the Kastanlustig self-dual basis element. But what we don't know, or what was the conjecture, so the conjecture, so that's a theorem. It's an algebra isomorphism. So now you have here the basis given by the indecomposable objects. And here you have the Kastanlustig self-dual basis, and you see it's very easy to calculate it for the identity element and the simple reflection. These things correspond. So the conjecture of Zergel was the following: that the character of BW is the Kastanlustig self-dual element. Okay. So, and now if you look at the construction, you see that this makes sense almost immediately for an arbitrary Coxeter system. You just need to replace the Cartan algebra. And this is what Zergel did. He defined a so-called reflection faithful representation of a Coxeter system of an arbitrary Coxeter system over the real numbers. And he took this as the symmetric algebra over this space as S. And then you define just to write down the same definitions. The theorem is still true, and the conjecture in the arbitrary, in the general case, was open, because so this conjecture is proven by Zergel. So let me. I mean, this deserves more space. So let me. Let me write down some facts about this conjecture. So what I explained in the last lecture is the following. So this conjecture of Sergel is equivalent to the Kashtan-Lustig conjecture. Yeah?
In the character that you wrote down,
In the
character of BW,
yeah,
of the Sergel decomposable BW,
yeah,
there was a sum on the right side with X in W.
yeah.
The question is, will the sum, can you just take it over X less than or equal to W?
Yes, yes, absolutely. Yeah, yeah,
So
yeah.
only
So
those
this
count.
only those count. Yeah, yeah, absolutely. This is equivalent to the Kashtan-Lustig conjecture. Makes sense. Using reflection faithful representations. So it is proven by Sergel for crystallographic systems. Crystallographic root system. Crystallographic. So for Weyl groups, right? So what? For Weyl groups. It's proven by Sergel for Weyl groups. Okay, it's equivalent to Kashtan-Lustig conjecture, and there were already proofs. But so the idea is to realize BW as equivariant intersection cohomology complexes. Simple perverse sheaves. So equivariant version of a simple perverse sheaves. So it's proven by Sergel for Weyl groups, proven by Elias and Williamson for arbitrary W, Coxeter systems. And you see the difference between a Weyl group and an arbitrary Coxeter system is that for a Weyl group there is a representation theory and a geometry, but not for an arbitrary Coxeter system. Okay, and yeah.
Okay, sorry, maybe we have to finish and then ask.
Yeah, so the last remark, so if you replace C by FP bar, or, I mean, so the action of the Weyl group on a symmetric algebra is, I mean, it is, how should I say, it's defined over the integers. That means it doesn't matter if here you have C or the real numbers or the rational numbers. The only thing that really is important is the prime field of the field U. So it really depends only on the characteristic. So if you prove it for one field in characteristic P, then you prove it for all fields. So if you replace C by FP, then Sergel showed that this is equivalent to part of Lustig's conjecture. And the part of Lustig's conjecture is the following. So if you look at the alcoves in, oh, that's a really bad drawing, but well, okay, let me start over. So if you look at the dominant Weyl chamber, then you have a Steinberg weight there, and you have set of alcoves that contain the Steinberg weight in their closure. So that is parameterized by the finite Weyl group, and you can ask about the. So you take a Weyl module here, and you ask not about you want to calculate not all Jordan-Hölder decomposition factors, but only those that correspond to this finite Weyl group orbit. This gives a certain sub-quotient category in the category of all representations of the group. So these are the representations that contain only those simple modules in their Jordan-Hölder decomposition, Jordan-Hölder series. And so this is a small sub-quotient category of all representations. And then you can formulate what Lustig's conjecture means for those. And this part of Lustig's conjecture is then translated in Sergel bimodule language by Sergel, and you get the same conjecture. You just have to replace the complex numbers by FP bar. And this is only a part, but I mean it's the relevant toy model for all our approaches. If you want the whole of Lustig's conjecture, you have to replace everything by moment graphs.
Sorry, question. So,
yeah?
But everything is about finite Weyl here.
Yeah, here it's everything about the finite Weyl group. The moment graphs will then use the affine Weyl group. Okay.
So is this, what is the status of this part of the conjecture?
Right, this is wrong. This part of the conjecture. So, okay. So this conjecture, it's kind of clear that if you look at this in positive characteristic, the characteristic should be at least the Coxeter number. I have to say, I mean, from the Coxeter number doesn't really appear here. No, I have to say, I mean, from this perspective, the Coxeter number would from the beginning not be a reasonable bound. So the Coxeter number, as I might have mentioned before, let me talk about this later. Okay. Well, anyway, Sergel stated, he didn't conjecture in his paper. He didn't conjecture. He conjectured this only for complex, for the real numbers in characteristic 0. And then I think there's a remark that it would be interesting to know this in positive characteristic. But looking at Lustig's conjecture, the real bound should be the Coxeter number. So what is the status of this? I mean, Williamson disproved this conjecture for prime numbers above the Coxeter number. And his results suggest that the bound grows with the rank of the Coxeters of the Weyl group in this case.
That is the bound for which this conjecture is true.
Yeah.
Sorted.
Yeah. I gave an upper bound for the validity of this, which is exponential in the rank. But my results also work in the affine situation, so they capture the whole of Lustig's conjecture. Okay, let me just.
One question on
Yeah.
Elias extension.
Yeah.
So, I mean, there are only the dihedral groups and H3 and H4.
Yeah.
So, even for the dihedral groups, I mean, presumably for H3, is the problem for H3 and H4 or the infinitely many dihedral groups?
Well,
I mean,
I think
H3 and H4 you could do by hand.
I doubt it. So maybe I don't know. I don't know if I don't know of any direct calculation by hand. But even for the dihedral groups, it's this. Even so, they have a quite simple structure. You would think it's not clear.
But certainly you can't go beyond Lukatson groups, right? I mean, pseudo-Lukatson groups are not enough.
Yeah. So I mean, you have this.
Separate Todd and others.
So no, there are no generalizations beyond Coxeter groups. I mean, you could. I mean, everything. So you see, these are coherent sheaves on a kind of hyperplanar arrangement. And you could ask, well, does that make sense for an arbitrary hyperplane arrangement? But then you have you have the reflection group acting, and so there's no obvious generalization. And there's, for example, also no generalization that I know for complex reflection groups. Right. We'll have tea probably in 5 minutes. So let me just finish by another remark. So in characteristic P, so I just write it down. So there are counterexamples. By Williamson in positive characteristic. But, you know, so the multiplicity 1 conjecture, the multiplicity 1 case, this would say, so that would state the following. So the graded rank of this homomorphism space this is 1 if and only if the corresponding Kashtan-Lustig polynomial, which in Zerger's notation is denoted by H, XW. This is true if the characteristic of K is bigger than the Coxeter number. So that is my multiplicity 1 result. And finally, okay, there's an upper bound is exponential in the rank. For the exceptional primes, for the exceptional characteristics. By these I mean the characteristics for which the conjecture is not true. There's an upper bound which is exponential in the rank. You see, these were my 2 results that I got in between 2007 and 2009, and that was the only result that was valid, you know, above the Coxeter number. So this gave some hope at that time that Lustig's conjecture is true. Of course, then multiplicity 1 doesn't occur so often, so it's not a very strong result in the end, but it was the only one that got down to the Coxeter number, and then it was complemented by this upper bound. But now we have counterexamples. So that is the state of the theory as far as I know it. And I should also say for all these results, you don't really need representation theory or geometry. So Elias and Williamson work without any geometry, even though their methods are highly inspired by geometry. I mean, as I said, they translate the geometric proof into his Zergel bimodule picture. And this upper bound, for example, at that time, it used the fact that the conjecture is true in characteristic 0. Okay, so what I will do after the break is I will introduce the moment graph picture, because this gives yet another view on this problem, and it kind of gives another description of this S module, of this graded S module, and it is easily generalized to the affine situation. So these indecomposable objects, they can be constructed directly without using tensor products or anything. And I can then motivate parts of the Elias-Williamson proof. So I can show you what kind of the main steps are in the Elias-Williamson proof. But I guess we'll start with that after the break. So I just now in the break, I was reminded of two things that maybe I should mention here, because there's also important. One is the duality, and the other thing is the occurrence of Bott-Samuelson modules. And so let me just quickly mention what the duality is. So so there's duality which is taking homomorphisms in the category of graded. So graded homomorphisms from something to delta E. So I mean, this is just S as an S bimodule, and this preserves the category of Zergel bimodules. So if you apply to a Zergel bimodule, you arrive at a Zergel bimodule, and so you can prove that these indecomposables are self-dual. And here you have to be careful with the shift. I think I shifted this by length of W, and this is in order to make it self-dual. Otherwise, this duality, so if you have apply the duality to a shifted module, you get the dual of the module shifted by minus n. So so you have to be careful.
Preserves means what you apply. The module itself you now think of as an S tensor S.
Right, and it's isomorphic to a direct sum of Bott-Samuelson modules again. It's again a Zergel bimodule.
So one could think of this circularity as just the fact that the Kashtan polynomials are
Right. So right, that is the the character. You have to be careful. For this, you really have to apply this character only to Bott-Samuelson module. To a Zergel bimodule. If you so let's say it like this: the character of a dual of Zergel bimodule is the dual of the. So it's I think I wrote this as an overline. No, maybe this I used this notation. So this is the duality in the Kashtan-Lustig duality in the Hecke algebra. So if B is a Zergel bimodule. For example, it doesn't hold for so it doesn't hold for this delta axis. This is not the same as if you apply the involution in the Hecke algebra. And these are not Zergel bimodules, just the standard modules. So this intertwines the duality, and this implies that the characters of the indecomposable modules, if you take all of them, then this is a subset in the Hecke algebra. This is also a self-dual basis. It's also a self-dual basis. So Jordi Williamson defined the P standard basis. So he added a P there. This is the character of BW, where this is defined over FP. And this he calls the P canonical basis. So then there was, a very short hope at one time, but so that in some cases there's only one self-dual basis with the appropriate normalization assumptions. For example, I think you can calculate that until A6 or A7 or so, this uniquely defines a self-dual basis, and then you could prove the Cauchy-Lustig conjecture directly. But then in A8 and higher rank, so then there are several self-dual bases. What did it? So sorry.
So the idea is, instead of Cauchy-Lustig polynomials, you look at the character of this.
Yeah, right.
And that should have the same property that you expect Cauchy. So it's a modified Cauchy.
Right, right. So it's self-dual, so it gives another self-dual basis. But it's not known what this basis is. It has certain other properties coming from right multiplications with H underlined S. And I should say these properties are enough to, in some cases, uniquely determine this basis. And this gives a kind of combinatorial or simple proof for Cauchy-Lustig conjectures in very low rank. But in A8 or so, it doesn't work anymore.
Couldn't you replace the Cauchy-Lustig polynomial in the Lustig conjecture by this polynomial? Expect a modified conjecture.
Well, morally, this basis gives you the character formula for the irreducibles. This
that is already okay.
this is let's say it's almost proven. It's so it's proven for the Steinberg. For the Zergel category around the Steinberg weight. If you know this basis, you know the irreducible, you know the multiplicities in Zergel's subquotient category. And it's expected that this basis calculates the irreducible characters in all cases. But this is not...
That's Lustig conjecture proof, right?
Well,
not Lustig, modified Lustig.
Right, it gives a character formula, and Lustig's conjecture would then be translated into the fact that this is the Kashtan-Lustig self-dual basis. You see, I mean, now you have these two bases, the Kashtan-Lustig self-dual basis and this p-canonical self-dual basis, and you hope that they coincide. And this is equivalent to Lustig's conjecture, modulo some yet unproven equivalence. So, am I confusing or?
No, not confusing. I'm a little puzzled because then we know that the original, I'm just asking, we know that the original Ricci conjecture is false.
Yes.
And then the Kashtan-Lustig polynomial in Lustig's conjecture being replaced by these p.
Oh.
Then it is true.
It's, something like, so, okay. Right. So the Lustig conjecture being false means that this does not coincide with the Kashtan-Lustig self-dual basis. So let's put a 0 here, in characteristic 0. That this is known that there's some p for which this basis is really different. So if I say you can calculate the character of an irreducible module when you know, as soon as you know this basis, it's, I think, a little bit more difficult than just replacing the polynomials appearing in Lustig sum formula by these polynomials. It's, so this is rather, this gives multiplicities, and then you have to invert these polynomials, and it's a little, it's more tricky. But it's possible. I mean, once you know this, you know the irreducible characters. But I cannot write.
Cannot write a formula like character of L lambda is not.
Not yet. I mean, this can be done, but it hasn't been done yet.
But this should still, I mean, if we don't think of the problem as calculating character of irreducible, but rather giving Jordan-Holder multiplicities.
Yeah, yeah,
Then
yeah.
This is the polynomial, right? Is that what you're saying, or even that is not completely true?
So I'm sure it is true, but there's. So okay, what I have proven is the following. I've proven that, so in the general case. So what you say is true if you restrict yourself to Zergel subquotient category, but if you're interested in all the restricted irreducible representations, then I have proven the following: if this basis for the affine Weyl group coincides with the Kashtan-Lustig self-dual basis, then Lustig's conjecture is true. And I have not yet proven that if this does not coincide with the Kashtan-Lustig basis, it still gives the right Jordan-Holder multiplicities. This is unproven. So, I mean, there's some concepts how you can prove it, but it's certainly not written down and no full proof. Yeah, absolutely, absolutely.
So in some sense, forget Kashtan-Lustig polynomials. This is the correct thing.
This should give the Jordan-Holder multiplicities. So the polynomials appearing here, evaluated at 1, should give the Jordan-Holder multiplicities. But as I said, there's an open step yet.
Sorry, maybe we're sidetracking it, but then essentially the problem is solved. I mean, because it's not like the Kashtan-Lustig polynomials are easy to calculate either. They are also difficult to calculate. So,
Yeah, but you know
it's maybe more difficult to calculate, but in principle.
You see, the difference is that you can calculate the Kashtan-Lustig polynomials, but just looking at the Hacker algebra. There's an algorithm that gives you the Kashtan-Lustig self-dual basis and Kashtan-Lustig polynomials. But this, I mean, there's nothing. You see the definition. The definition is here. I mean, in order to know this element, you have to calculate this Zergel bimodule. So it's
the
just.
problem then is there a simple algorithm to calculate these polynomials, or some other algorithm to calculate?
Right, that would be great. I mean, if you you would solve the, you would completely solve the question about irreducible characters for reductive algebraic groups. Once you give an algorithm how to calculate these. It's right. Inside the Hecke algebra, that is everything everyone dreams of. Yeah, an algorithm it must depend on P. What I wanted to stress here is that it again gives a self-dual basis. That much we know, but we don't know anything else. So, okay. So there's a Bott-Samuelson variety associated to this collection of simple reflections. So this is a Bott-Samuelson variety. And it maps onto the flag variety, G mod B. And that's the flag variety. And now if you take the equivariant cohomology of this Bott-Samuelson variety, this has a structure of an S bimodule. This is an S bimodule, and it is yeah, right. I mean, it's. Oh, yeah. So it doesn't. It could be a reduced. I mean, the only thing that you really need is reduced expressions of any W in W. But
the image will be a Schubert variety.
Yeah, it will. Yeah, the image will be a union. I mean, if it's reduced, the image will be the corresponding Schubert variety. So let's call this pi. So this is a. I mean, this is a smooth projective variety. Its image is a Schubert variety, which is in general highly singular. And I mentioned that the indecomposable Sergel bimodules, they are given by intersection cohomology complexes on the Schubert variety. So the topological picture of this is the following. So you can push forward in the derived sense the constant sheaf on this Bott-Samuelson variety. So this is the constant sheaf. This is the constant sheaf with the C coefficients on a Bott-Samuelson variety. And this is now an element in, so this is an element in the derived category, in the equivariant derived category of sheaves on G mod B. And so you can, what should I say? So, yeah. This is the point where you apply the decomposition theorem. The decomposition theorem tells you something about what you obtain when you apply the push-forward functor to an IC complex, in this case, to the constant sheaf. So the decomposition theorem implies that in this case, this is inside this derived category a direct sum of IC complexes on Schubert varieties shifted in their degrees. What you get, I mean, up to shift, you prove that what you get is an IC complex. And this implies that this implies Sergel's conjecture. So why? Why? So well, you can prove that as an what should I say? Okay, you can prove that this decomposition, if you view this as an S bimodule, it just corresponds to the decomposition of the Bose-Samuelson module. I mean, this decomposition into indecomposable S bimodules corresponds to this decomposition. And now you know that an indecomposable direct summand is actually given by an IC complex up to shift. So this this implies, so how does it imply Sergel's conjecture? So first, the decomposition theorem implies that BW, so the decomposition theorem implies that BW, an indecomposable direct summand, is just given by an equivariant IC complex on a Schubert variety. So on BW, so this is what the decomposition theorem implies as an S bimodule.
This corresponds to BW corresponds to
Say it again.
BW corresponds to that.
Right. So right. So BW occurs as a direct summand here, and so what? Okay. So what I should say, this is a sheaf, and you take its cohomology. But I mean, if you take the cohomology, you can forget about this P lower star. So you get actually this. If you take the cohomology, you get an S bimodule, and the decomposition in this category corresponds to a decomposition of S bimodules. So why is that so helpful? The point is the following. So the Kastanlustig self-dual basis is characterized by two properties. First, it's self-dual. But the other one is that if you recall the definition, is that H underlined W. So I mean, this means that it. So recall that H underlined W is of the form HW plus sum over all smaller x than W. So it's an element in HW plus V ZV HX. So the important defining property of the self-dual basis is that the coefficients in front of this HX vanish, don't have a constant term. The defining definition of the IC complex is that if you restrict it, so the IC complex of this Schubert variety, so if you restrict this to the Schubert cell at X, then this is a constant. Constant now, I mean, up to, so direct sum of constant sheaves up to shifts in degree smaller than length of W plus length of X. And again, I'm sorry, you have to. I mean, this is probably not really correct. I didn't prepare this part. But what I want to say is that, I mean, this splits into a direct sum of constant sheaves, but the allowed shifts are bounded for the IC complex. For perverse sheaves, they are bounded, and there's a little bit a stronger bound for IC complexes. And this stronger bound gets translated into the fact that here we don't have a constant term. That's it. Once you know this is an IC complex, you get that here the character of BW, so that implies that the character of BW is of the form HW, so HW plus and then the same VZV HX. And this is the second characterization. So this, yeah. Okay.
Then I'm confused. Why is that a different cellular basis? Why do you say different cellular basis?
Where? Say it again.
You say character of BW.
Or you mean the p-canonical basis?
Ah, yeah.
That is
So
different. So this is. Oh, that is also. So that is only for the p-canonical basis.
so what I say here is that if you don't know anything about these BWs, the character I have defined before will the characters will form a self-dual basis in the Hecke algebra. So Jody calls it the p-canonical basis. If you construct these BWs over a field of characteristic P, it's a new basis, and you know it's self-dual, but this is exactly the property that you don't know. And this additional normation property comes from the fact that these BWs are actually IC complexes. And then the definition of the IC complex translates into exactly the right property for this p-canonical basis.
And that 15 degree says something, Holmes says that's not constant.
Yeah, yeah, exactly. This strictly smaller assumption here is translated, if you go through all the technical details here that I left out, is translated into the fact that here these polynomials don't have a constant term, a vanishing constant term. Yeah.
Another question.
Yeah.
So there are some small variants of the canonical basis, right? You can put some prime or something.
Ah, yeah.
So,
But
all those also are covered in, can you construct things that look like that in this?
oh yeah. So I think you can. So you have several choices. So for example, I looked in order to calculate the character. I looked at these Hom spaces. Right. I could also look at the dual Hom space. And then you get a kind of, you replace V by V2 minus 1.
That you can go on this side seem to have unlocks on the others.
Most of the constructions, and I have to say this, I had a PhD student, Martina Lanini, and her PhD thesis was about to lift identities of Kashtan-Lustig polynomials to a categorical level. So, you have some inversion properties, for example, for Kashtan-Lustig polynomials, and this you can see on the moment graph side as well. So she could prove that there's equivalences of moment graph sheaves that give these inversion properties for Kashtan-Lustig polynomials. So things like that happen. You cannot lift everything, but a lot can be lifted.
So in the category of circle bimodules, the fact that you have this category and Sorgel's theorem that these indecomposables which are uniquely characterized, Sorgel's theorem, the proof of that, what are the kinds of things that go in there? Is it purely opposite group and category theory?
No geometry, no representation theory. You can read Zergel's paper, bimodules over polynomial rings, or I forgot the title. It's appeared in the journal of the Institut Jussieu, Institut de Mathématiques de Jussieu. And there he defines this category, and he characterizes the bimodules. And this is, I mean, in some sense, elementary. I mean, it's difficult, but it's elementary in the sense that you don't need any other theory.
I don't know if I should say this, but for Sorgel's papers, usually somebody else needs to write another paper.
Right? Yeah.
People understand.
He writes very elegantly and sometimes very condensed. So I agree. So it's not easy to read. Okay. So I have half an hour, I think, and
You could go on, yes.
yeah. So let me finish circle bimodules for the moment and talk about moment graphs. So moment graphs appeared in geometry. I mean, that's mainly the paper of Goreski, Kottwitz, and McPherson, caudal duality and localization. But it has a lot of predecessors. So they come from localization theorems. Yes?
So, I wanted, so problem is that she came to the topological, lift it to algebraic geometry, what was done in topology, is that fair to say, or is that a correct description?
No, I think they generalized this. So what was done before is that you can calculate equivariant cohomology of a space using the skeleton of a T-orbit. And what Goreski, Kottwitz, and McPherson did, they generalized this to not only the cohomology, which is the cohomology of the constant sheaf, but the cohomology of so-called equivariantly formal sheaves. The intersection cohomology or parity sheaves being some of them. It's a kind of generalization. And let me start with this for a moment, just to motivate this. So you have a complex projective variety, or complex variety. With an action with a T action. So T is a torus. T is a torus, and we have this T action, and we have some assumptions, namely that there's finitely many fixed points and one-dimensional orbits. And let's assume it's projective. That makes life easier. I mean, yeah. In one-dimensional orbits. So this already gives a moment graph. So the moment graph appeared. I mean, it's called moment graph because it also appears as the image of the one skeleton of this torus section on a moment map. But you can define it directly as follows. So the vertices are fixed points. The edges are one-dimensional orbits. So how could these be considered as an edge? Well, an edge is just a pair of two vertices. And the idea is that one-dimensional orbit in this case will be isomorphic to C minus 0 with a linear action of T. With linear T action, and so if you form the closure, so if the orbit is E, you pick at two fixed points. I mean, the closure will then be, if you're working in a projective variety, will then be a P1. So this is the original orbit plus 0 and infinity, if you want. So this can be considered as an edge connecting the two fixed points. And then what you also need is a label. And this comes from choosing an isomorphism as here, and then T acts via a character alpha. So this gives the T action. This means that T acts on X by just multiplying it with alpha T for some alpha homomorphism from T to C cross. So that is our weight lattice. So all the one-dimensional orbits will be isomorphic to this situation where you have T acting just as multiplication with a scalar. And of course, the scalar, I mean, this is a group homomorphism from T to C cross. These are not well defined. For example, you can invert the parameter here, Z. You can replace that by Z to minus 1. This gives an automorphism here. And in this case, you would replace alpha by minus alpha. So this is a non-canonical moment graph, but nothing that we do will depend on the fact if you choose alpha or minus alpha. So this is the graph, and then so what do we do with this graph? So you see, this graph is a kind of is a one skeleton in this variety. You have these P1s sitting inside the variety, and you have a T action. So it might look like this. You have these fixed points here, and the action of T on these one-dimensional orbits. And now if you have an equivariant sheaf, so F, so we can do that in the derived category of sheaves on X, and we can choose a field of coefficients. So we are looking at sheaves of K vector spaces on the topological space underlying X. And then you can take the equivariant cohomology of this sheaf F at any fixed point. So this is the stalk at a fixed point. So if X is a fixed point, then you can consider the stalk of the sheaf at this fixed point and take the cohomology of this fixed point. This will be an S module, where here S is the symmetric algebra of the weight lattice, but where you extend the scalars to the field K of this K vector space. And also you can restrict it to a one-dimensional orbit. So this will be an S module as well. So E is in one-dimensional orbit. And this module will have the property that it's annihilated by by the label alpha. So if alpha is the character with which the weight with which the torus acts on the one-dimensional orbit, so it's kind of the speed of the rotation of this C cross, then this alpha will annihilate this this equivariant cohomology. I mean, this is a simple calculation. This is now a sheaf on C cross with this action of T given by alpha, and then you calculate what happens to the equivariant sheaves there. And what you also get is a map rho xe from the cohomology of the fixed point to the cohomology of the edge if X is contained in the closure of E. Well, how is this map constructed? So this is a kind of restriction map. It's constructed in the following way. So you see, X is in the closure of E, and you can, as a step in between, you can restrict your sheaf to the orbit and this one fixed point in the closure. So this will then be isomorphic to C, to an affine space of dimension 1. And so you can take the cohomology there on this affine space, and then because we are having we're taking cohomology, you can restrict it to both the fixed point and the one-dimensional orbit, and you prove that this is an isomorphism in the situations we consider. You prove that this is an isomorphism, you invert this, and then you, okay, this gives this map from this space to this space. So now what did Goreski, Kottowitz, McPherson prove? So what we constructed here is actually what is then called a sheaf von graph. S module, then you can calculate it in the following way. So it sits inside the direct sum of the cohomologies on the fixed points. So it's a subset inside here, such that rho xe of mx equals rho ye of my for all one-dimensional orbits of course they must have x and y in their closure. Okay. Okay. So you see, this rho xe is defined here. The claim here is that the global cohomology of the sheaf sits inside the direct sum of the local cohomologies on the fixed points. The map from here to this direct sum is very easily constructed because x is a fixed point. The pullback to a fixed point yields a map of the global cohomology to the local cohomology. And then you take the direct sum of these maps. Take the direct sum of these maps, you have a map from the global cohomology to this direct sum. And the first thing that you have to prove is that the direct sum of these maps is injective. And then you describe the image. And the image is given by exactly this. So this is the localization theorem.
Say maybe just one or two sentences
Yes?
on what is involved in the proof of this.
Oh, right. So yeah. So the proof of this is a lemma of Jung and Skjelbred. Jung and Skjelbred. So the injectivity so yeah, the injectivity is proven in the following way. You describe the kernel of this map, and you prove that it's a torsion. So it's a torsion S module. But the kernel has to sit inside this free module, and there's no torsion submodule, so it must be injective. Part one. And then you localize the situation on so you see we restrict here we restrict the whole sheaf on the one skeleton of the torus action, only in fixed point and one-dimensional orbits. This is enough to calculate these numbers. But you could also restrict it to just to one-dimensional orbits associated to let's say okay, so so once you know that this is a subset here, you first prove that it's actually contained in the subset where you only consider rho xe and rho ye for edges going into a certain direction, where you specify alpha, and then you have a kind of SL2 situation. I mean, SL2 is not visible there, and then you form the intersection, and then there's a theorem that that says that the co-kernel of this intersection. I mean, it's mainly Chang-Skjelbred, lemma of Chang-Skjelbred that says that you actually, if you form the intersection, you get everything. I mean, you get the whole, you don't get more than the global cohomology. Okay. So now this motivates the definition of a moment graph sheaf. So you see now this gives a very convenient, very simple way to calculate global cohomology of sheaves if you know these data, the local cohomologies and these row maps. And the question, of course, is can we, for important class of sheaves, can we give these data kind of intrinsically on the moment graph? And so let me first define what a sheaf on the moment graph is. So on this moment graph, so it's given by, so it's an object F. So it has components Fx, Fe, and rho xe. And so Fx is a free S module. No, it's just an arbitrary S module. Fe is an S modulo alpha E S module. And rho xe is a homomorphism of S modules. Homomorphism of S modules. That's exactly what you get from an equivariant sheaf on this variety X. So now, if F is the intersection cohomology, the equivariant intersection cohomology of X, say of X. I mean, now X was a arbitrary projective variety. We should restrict to the case where X is a Schubert variety. Then this gives a sheaf that we call WF. The construction is as before, the construction I outlined. So W is actually a functor from derived category of equivariant sheaves to sheaves on the moment graph. In this case, WICT X is described by Braden McPherson. By Braden, who is a student of McPherson and McPherson himself. And they gave an algorithm to calculate this sheaf on the moment graph, the sheaf that you obtain from the IC complex. So, so this is the Braden-McPherson sheaf. And they did this in the case where the field is of characteristic 0, and so, and then, I mean, you might expect that the same statement holds in positive characteristic, but it's not yet true. Together with Geordie, so we proved that W of what is called a parity sheaf is given by the Braden-McPherson algorithm. If the characteristic of K is positive, again with these exceptions that I mentioned before. So it's this class of parity sheaves on such a variety that localizes to a Braden-McPherson sheaf. Okay. Let's see. Let me so should I define what a Braden-McPherson sheaf is? It's again a little technical, or shall I give the relation to representation theory? So this is a topological side. The relation to okay. So here you see we have the category of parity sheaves, and then there's this functor W that's just taking local cohomology and constructing these row maps that gives Braden-McPherson sheaves. So and then from representation theory, you plug in projective objects in the category O, or in the category C. This category C is the modular version of category O that we talked about. You get a homomorph. I mean, okay, that's a little. You get a map from here to here, and this is the map v to the -1. The functor v to the -1. So let me simplify this a little and not talk about the modular case. I mean, so if I talk about category O, you can go in this direction. Because in positive characteristics, this won't be an equivalence. This is maybe the nicer thing to explain. So in characteristic 0. So how is that? How does that work? So we have this functor v from the deformed category O, say the principal block, to modules over the endomorphism ring of the anti-dominant projective. And we have seen this gives circle bimodules when you plug in projective objects. But this endomorphism ring, this turns out to be also isomorphic to the structure algebra Z of the moment graph underlying the principal block. This this is the graph I mentioned before. You know, the vertices are the elements of the Y group. The edges are given by reflections. The labels are given by co-roots. So the endomorphism ring is the structure algebra of this moment graph. I can say something about the proof of this statement in the next lecture tomorrow, but let me just outline how you get to Braden-McPherson sheaves. So now there's a theorem. Or let me first construct something else. So on so for every moment graph sheaf, there's a global section functor. So for every moment graph sheaf, you can form global sections. So this goes from moment graph sheaves to Z modules. Modules over the structure algebra. I mean, this is very much like in sheaf theory. For example, moment graph sheaves can be considered as coherent modules over a certain topological space, and so the global sections of the structure sheaf of this topological space is just Z. This really fits into a sheaf theory picture. So you get Z modules, and now what you define here is a certain subcategory. These are the sheaves admitting Verma flag. Sheaves admitting a Verma flag. And this means, this condition means that local sections are free S modules. That is the condition that is fulfilled by sheaves admitting a Verma flag. That's the definition of admitting a Verma flag, so that local sections give free modules. And it turns out that the Braden-McPherson sheaves here. In this situation, they do admit the Verma flag, and these are the projective objects. So for this, you construct an exact structure on this category. So then you can talk about projective objects, and the projective sheaves in this context are the Braden-McPherson sheaves. That's a theorem that you have to prove. And so once you know this, you prove that. So you see now we have two functors, namely a functor from sheaves admitting a Verma flag to Z modules, and from category O, and let me restrict to modules admitting a Verma flag. Inside this deformed category O. So you have these two functors, global sections, and a version of Zergel's structure functor, and you prove that they have the same image. So this means this gives an equivalence. And this equivalence is even exact. This means the projective objects here correspond to the projective objects here. Here, these are the projective objects we are interested in. They're Verma multiplicities, and here we have the Braden-McPherson sheaves. So as a corollary of this is that we get that if you apply V to a projective object, you get the global sections of the Braden-McPherson sheaf for W, using this exact equivalence. And okay, to finish, you see, taking this together now gives this picture. These are both W and V are fully faithful functors, and this means you get a connection between projective objects in O and parity sheaves. So these are fully faithful, so equivalents of categories, and you have this this equivalence. Projective objects in O are parity sheaves. Okay, that was a kind of a very quick overview of this subject. But this is the background. I think in the talk tomorrow, in the lecture tomorrow, I should talk about Moen graph sheaves and about the constructions, the methods that Elias and Williamson used to prove all the conjectures. I mean, now you have the the relations between representation theory, geometry, and sheaf theory, or Zergel bimodules. That's also here. And then tomorrow we can maybe in more detail describe the methods and constructions that Jordi and Ben used. Okay, thank you very much.